Okay. All right. What you got there, Jack? Show everybody your whiteboard. Now you've added stuff since I was last over there. Yeah. Because like you had the right answer to begin with, then you didn't have anything else. The right answer is not that important to me. All right, so I'm anxious to see what you add. All right, so first off, Jack, what's your group think? Is it easier to pull up or to push down? Pull. It's easier to pull up. I'll show everybody how come. Josh, heads up so everybody can see.
So when you're pushing it, you have the. So when you're pushing it, you have the vertical component pushing down, which in turn increases the normal force, which in turn increases the force of friction. But when you're pulling, you actually have a component force pulling up, so which in turn decreases the normal force and then decreases the force of friction.
Yeah. So they first started, all they had was these words, right? And I let them be, right? They had the right answer, but I was hoping to make an example of them. They corrected themselves, all right? Now that group had some diagrams right off the bat. This group had the best diagrams, right? The idea, again, is that we're solving this using our diagrams and our idea to think and to reason, okay? So here's what we're going to do here. We're going to come back, and let's hand in our test corrections at the end of class. So erase that, come on back, and we're going to talk about these diagrams and then do a couple math examples for us, okay? So essentially, this all starts with our ability and desire to draw our force diagrams, and then we can, we can work with our answer based on those diagrams. Okay, so now look at it. This group did a nice job because they included pulling straight across, right? So if I'm pulling this thing straight across, parallel to the ground, then the force diagram looks like this. I've got some force this way. It's pulling it. I've got a force of friction that is opposing the motion of the sled. Then I've got weight down, and we've got the normal force upwards. Now, Lauren, I think, did a nice job of explaining. Like at the very top of your reasoning pyramid, right? There's got to be one thing that you're doing, and one reason why you're doing all this stuff. And Lauren, what was that one reason? That's not what you said, right? Like it goes higher than that. Like which sled's easier to pull? The one with the smaller force of friction. So at the top, well, all things other considered, right? So if we think of the top of the pyramid, like we're looking for reasons to describe which one has the lowest amount of friction. Well, what is the force of friction? The force of friction is mu times our normal force. Now, if we just isolate this one, so we keep all other things the same, right? Whether this lady is pulling this guy angled up, angled across, or pushing down on his back, the two surfaces involved are still the exact same surfaces, which means our mu isn't going to change. So how are we looking to describe a lower amount of friction? Well, it's going to be the situation that has the smaller normal force. Well, in this particular case, since there's no vertical acceleration, we know that the normal force must equal the weight of the person. So at the top of our pyramid is, hey, which one of these things has the largest weight? Which one of these has the largest normal force / the smallest normal force? Then now we've started our comparisons. Okay? Well, now, what about this picture right here? The person is angling this push down. So this force is angled downwards. There's still a force of friction that is hindering this motion. The ground is still pushing upwards, and the weight of the object is still pushing down. Now, if we pull up or pull across or push down, does that ever change this person's weight? No, it never changes that person's weight. So we know that this weight is the same as that weight. Now, it's a little bit harder to analyze this diagram. In fact, something about that diagram necessitates for us a second diagram. What about this diagram necessitates a second diagram, Sammy?
There is a vertical component to the force.
Yeah, this thing has a vertical and a horizontal component. And this force is not either parallel or perpendicular to the surface that the sled is on, which means we have to break it into its components. So we've got Fx here, we've got Fy here. We still have the weight of the sled, the ground's still pushing up, and the force of friction is still that way. Again, at the top of the pyramid, which one of these things has the lowest amount of friction? The thing with the lowest amount of friction is going to have the lowest normal force because the coefficient is the same for each of the surfaces. Well, the normal force is in the vertical here. Well, in this particular case, since there's no acceleration upwards, we know that Fy, the normal force must equal, let's leave it exactly in the same, must equal W plus Fy. Well, look at the comparisons here. If this equals the weight, this equals the weight plus the push, the force for the push going down. This is going to have a bigger normal force and consequently going to be more difficult to push across. And then you can kind of get the understanding that the opposite is going to happen if we're pulling this thing upwards, right? If she pulls up like that, we still have a normal force, we still have weight, and we still have the force of friction. The values might change a little bit, but the characteristics of the force are the same. We have the same problem here. This thing's at an angle, right? That thing's at an angle, which means, hey, I got to break that into its components. Well, now we've got Fy going upwards instead of down over here. And that's going to change things for us. Fx there, W there, force of friction here. And then, of course, then the normal force here is going to be the weight minus Fy. So if our choices are that we want to limit the amount of friction by limiting the normal force, this normal force is the weight, this is the weight plus something else, and this is the weight minus something else, then this is our winner right here. By lifting up on the sled, we're creating a less of a frictional effect here, making this easier in terms of a friction perspective, right? I mean, we can argue physiologically and stuff like that, but from a friction perspective, that makes this thing easy. All right, so now, we've been working with slanted surfaces. Now, our surface is flat, but our actual force is at an angle. But it's the same setup, right? It's the same setup. If I've got this force angled like this, if this is my force F, and it's angled at some angle theta, then as per exactly what we did with this wiffle ball, we know we've got an x component here. Let's label that Fx. I've got a y component here. Let's label it Fy. I know that this side of the triangle is the adjacent side, so that Fx is going to be the full force times the cosine of theta, and Fy is going to be the full force times the sine of theta. And from there, we move on and we do stuff exactly like we've been doing it up till this point. We just have a new set of tools that we can use in particular situations. So if we have a new set of tools to use in a particular situation, then we can handle this problem here. All right, now this is posted out online, so that we don't have to waste time in here, copying this thing. Right, so later you can go back and copy it if you want. All right, can you read, can you read this for me?
Joe is pulling a 5-kilogram wagon filled with 20 kilograms of rocks down the street. He pulls on the handle of the wagon with a force of 40 newtons, and the handle is at an angle of 35 degrees before it mounts. If we neglect the effect of friction, what is the acceleration of the wagon?
All right, so read, are we dealing with, the situation on the left, in the middle, or over on the right? And as far as the handle in the wagon is concerned.
We're on the right.
Yeah, we're on the right. Now, what is different about this problem compared to the situation we have over there on the right? Yeah, let's make it easy on ourselves to start with here. Right? Here's our situation. I've got this force pulling this way. I've got the normal force up this way. Weight going down. Because it's a wagon, we can kind of pretend a little bit easier that there is no friction. Mostly, this is to make our math a little bit easier for us. Well, this force we can't deal with. Right? That force has to get broken into its x components here. F sub x. It's got a y component here, f sub y. It's got the normal force there. And it's got the weight going down. Now, we got our picture. What's the next thing we got to figure out? Got our picture. What's the next thing we got to figure out? Carl. What is the thing at equilibrium? So, Carl, what's the important words here? What is the acceleration of the wagon? So that tells us no equilibrium. How are we going to start this, Carl? Sum of the forces equals m times a. Now look at it. We got to worry about this idea of the sum of the forces, both vertically and horizontally. But in this particular case, because the motion of the object is in the horizontal, and in reality, we only want to worry about what's happening in the x-plane. Which means, how many forces are there in the x-plane in this particular case? Only one force, right? So Fx is equal to m times a. What are we trying to find here, Josh? Wow, overall, what are we trying to find? Yeah, A, so then we start the process that you've already jumped ahead in, right? We know the M. Do we know Fx? Well, if we did, we'd be done. We don't know Fx. What can we substitute in for Fx? Lauren? F times the cosine. I'm going to just use symbols, but basically, yes. And we start the process all over again. We're looking for A. M is 25. Theta is 35. And F is 40. Do we know everything other than A? Now we solve algebraically so that F cosine theta divided by M is equal to A, and there's our answer. Now in this particular case, we can plug numbers in. I'm not worried about the numbers so much because this would likely be our answer on an AP exam. Maybe if it's a part 2 question, maybe you're going to plug the numbers in, but maybe not. Huh? Now, that's a pretty easy one to start, but as we know, what happens? They always get more complicated, right? But if we follow our same setup, then we're good to go. All right? Laura, read this for me, would you?
What is mu? If a 300 Newton force.
Well, stop it right there. All right? That's a secondary question. We're here to start with. All right? Our question is, what is mu? Mu is the coefficient of friction. All right? We got to find the value for mu here. But what's important for us to understand is we don't start this any different than we've been starting stuff for a month. We got to get our picture, in which case, our picture's right here already. We've already done it. We're pushing this crate downwards, all right, across the... Oh, I reached the wrong thing. Son of a gun. Well, we're going to have to do it all over again. All I erased the wrong one. So there we go. There's our push downwards. I should have left the middle one. That force is no good though, because it's at an angle. So now I gotta switch my picture. That force has an x component F sub x. It's got a normal force going upwards. Friction is opposing that motion. That force has got a y component, and of course, the weight of the crate is always going down. No matter what the question is, we're still always starting this exactly the same way we always do. Now, Carl said we got to figure out whether this thing's in equilibrium or not. Carl, is this thing in equilibrium?
Yeah.
Yes, correct. How do you know? Constant speed means equilibrium, which means, Kyle, how are we going to start this problem here? Sum of the forces equals 0. Now, for us, it's important for us to understand here, this thing is in equilibrium, both vertically and horizontally, right? So the sum of these forces is 0, and the sum of these forces is 0. But we don't want any randomness in terms of how we solve this. We are after mu. So would we worry about the horizontal forces or the vertical forces? Horizontal. Sammy, how can we worry about the horizontal? Yeah, where's it buried though? Yeah, mu is buried in there. So we're going to have to use this stuff to get us started. Josh, can you give me an expression for the sum of the forces acting in the horizontal here? Awesome. Fx minus Ff equals 0. Rachel, is there anything else he could have said? Ooh, okay. So, as Sammy said here, we need to get mu. Mu is buried in here. So we're going to substitute mu times Fn for Ff. Like this is the way to start this, but there's a fundamental problem with that line. The fundamental problem with that line is that the thing we're looking to find wasn't in there. Now we're in business. Now we go about it just the same way we did over here. In other words, we're looking for this, so it's okay for it to be in there. Are we told the value of Fx in this particular thing? No. Sam W, what do I replace Fx with? Yeah, force times the cosine of theta. Now be careful with that, right? Every situation you would want to specify based on the situation. What's this say? It says the force is being exerted at an angle of 20 degrees below the horizontal. What the heck does that even mean? Well, here's the horizontal. It means the force is being exerted down here. So that angle there is 20 degrees. Well, if I'm looking for the x component and I want to, use my trig triangle, there's the x component, which means it's adjacent to the 20 degrees, which means f times the cosine of theta can replace f of x. Now we evaluate this expression. I'm looking for mu. Do we know the value of the force that this person pushes with? What do they push with? 300 newtons, so we're good. The angle is 20 degrees below the horizontal. So we know f, we know theta, we know mu, or we don't know mu, but it's okay because that's what we're looking for. Do we know the value of the normal force? No. What can I replace the normal force with? Josh. Boom, Fy plus W. So, F cos theta minus mu times Fy plus W equals 0. Start everything all over again. 300 is our value for force, I think. Yep. 20 degrees. It's okay that we don't know this. Do we know the value of Fy? No. What do we replace Fy with? Well, F sine theta. F cosine theta minus mu times f, mu times f sine theta plus w equals 0. Okay, same process. Looking for mu. It's okay that we don't know that. 320 degrees, 320 degrees. Do we know the value of the weight of the crate? Yeah, we don't. Lots of times we have to substitute m times g. Do we have to do that here? No, because 1,000 Newton crate, that's the weight of the crate. Do we now know everything we need to know to figure out mu? Yeah, now it's algebra. I take this entire thing over here and then divide by what's in the parentheses, and I end up with f cosine theta divided by f sine theta plus w, and that is my answer for mu. And that I find like beautiful. I think it's just awesome, right? You can plug those numbers in, you can get an answer from mu. I'm not worried about that answer. I'm worried about that algebraic expression. Right? And I love the fact that we get it the exact same way that we've been doing the other stuff. Okay. Now, that, as Kyle told us, is for an object in equilibrium.
Wait, wouldn't that box just not be moving?
What do you mean?
It's pushing like 300 newtons.
Yeah, this
20
is.
degrees downwards. That yeah, you wouldn't be moving.
Why not?
The box is 1,000 newtons.
I just made up the numbers. You know,
Oh.
but remember, you're not trying to overcome 1,000 newtons. You're trying to overcome the friction that 1,000 newtons creates.
Yeah.
So if you have a 1,000 Newton thing on ice, this is super small. That's all. You know what I mean? If you have a 1,000 Newton crate on some sand, like yeah, maybe these numbers don't necessarily work out. But remember, and this was one of the problems we had on that part 2, question 2. The weight of that falling object in that question was not trying to overcome the weight of the object. It's trying to overcome the frictional force on that object. And in that question, there was no frictional force, right? So this does not have to be bigger than this. It's just got to be bigger than the friction force that it's going against. Huh? Actually, in this case, it only has to be the same speed. Now, if we pull up instead of down, why is the object going to accelerate? If we push down, it moved at a constant speed. If we pull up instead of push down, why is the object going to accelerate? Lauren, give it one.
Because when you pull up, the normal force is less, so then the friction force will also be less.
Perfect. If there's an acceleration, I can't start with sum of the forces equals 0. What do I got to start with? Sum of the forces equals mf. Now it's still, then it's got the same stuff. Fx minus ff is now equal to ma. Notice we've got a lot of similarities. Now we're trying to find the acceleration. We got to know all this other stuff. We got to do all of our replacing, right? Let's do it all in one full swoop. What do we replace fx with? F times the cosine of theta. What do we replace ff with? Mu. Now we're pulling up. So what's the normal force going to be equal to? W minus F sine theta. We would have known this. We know this. We know this. Ooh, W, what do you got to replace W with? Oh, nothing. Oh, what do we got to replace M with? W over G, right? So F cos theta minus mu times W minus F sine theta. W equals W divided by G times A. Know it. Figure out A. So we can do all sorts of different stuff if we have these basic principles. Oh, test corrections. Drop those test corrections for me right here on your way out.